Okay, today we're looking at section 7.8, the addition rule for probability. So up to this point, we've looked at probabilities of simple events, one thing. Simple events are those with a single simple characterization. Sometimes, though, we want to investigate more complicated situations. For example, if we are choosing a college student at random, we might want to find the probability the chosen student is a varsity athlete or in a Greek organization. This is a compound event. There are two possible criteria that might be met. We might instead try to identify the probability that the chosen student is both a varsity athlete and in a Greek organization. In this section and the next, we'll cover probabilities of two types of compound events, those using or and those built using and. We'll deal with the former first. So mutual exclusivity. Before we get to the key techniques of this section, we must first introduce some new terminology. Let's say you're drawing a card with a standard deck. We'll consider three events. There's the event H, the card is a heart, T is the event, the card is a 10, and S is the event, the card is a spade. If the card drawn is a jack of spades, then H and T didn't occur, but S did. If the card drawn is instead a 10 of spades, then H didn't occur, but both T and S did. You see from these examples that if we are interested in several possible events, more than one of them can occur simultaneously, both T and S, for example. But if you think about all the possible outcomes, you can see that H and S can never occur simultaneously. There are no cards in the decks that are both hearts and spades. Pairs of events that cannot both occur simultaneously are called mutually exclusive. So, suppose you're about to draw one card from a deck containing only these 10 cards. Ace of spades, ace of hearts, ace of clubs, ace of diamonds, king of spades, king of clubs, queen of hearts, queen of spades, jack of hearts, and jack of spades. Decide whether these events are mutually exclusive. E is the event the card is an ace, and F is the event the card is a king. Can a card be both an ace and a king? No. So these are mutually exclusive. R is the event the card is a heart, and E is the event the card is an ace. We have an ace of hearts. So these are not mutually exclusive. R is the event the card is a heart. F is the event the card is a king. This is mutually exclusive. And that brings us to the formula, the addition rule for mutually exclusive events. If two events are mutually exclusive, then we can use addition to find the probability that one or the other event occurs. If E and F are mutually exclusive events, then the probability of E or F is the probability of E plus the probability of F. So why does this work? So let's look at a basic example. Suppose we're about to draw a Scrabble tile from a bag containing A, A, B, E, 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 R, S, S, U. What is the probability of drawing an E or an S? Since 3 tiles are marked with E and 2 are marked with S, there are 5 tiles that satisfy the criteria. There are 10 tiles in the bag, so the probability is 5/10 or 1/2. Notice the probability of drawing an E is 3/10, and the probability of drawing an S is 2/10. Adding those together, we get 3/10 plus 2/10 equals 5/10. And look at the numerators and the fractions involved in the sum. The 3 represents the number of E tiles. The 2 represents the number of S tiles. This is why the addition rule works. Total number of outcomes in one event or the other is the sum of the numbers of outcomes in each individual events. Suppose you're about to draw one card from a deck containing only these 10 cards. Ace of hearts, ace of spades, ace of clubs, ace of diamonds, king of spades, king of clubs, queen of hearts, queen of spades, jack of hearts, and jack of spades. If appropriate, use the addition rule to find the probability that one or the other of these events occurs. E is the event the card is an ace. How many aces did we have? 1, 2, 3, 4. So the probability of getting an ace is 4/10. And F is the event the card is a king. How many kings did we have? 1, 2. Probability of a king is 2/10. Add them together, we get 6/10 or 3/5. R is the event the card is a heart, and E is the event the card is an ace. I have an ace of hearts, so these are not mutually exclusive. So using this method, we cannot calculate that. R is the event the card is a heart, and F is the event the card is a king. So how many hearts did we have? 3. The probability of a heart is 10. Probability there were 2 kings. And note, we have a king of spades and a king of clubs, but not a king of hearts. 5/10 or 1/2. So what about events that are not mutually exclusive? So let's return to our initial example. Drawing a Scrabble tile from a bag containing A, B, E, R, S, U. Consider these events. J is draw a vowel, and K is draw a letter that comes after L in the alphabet. Since there are 6 vowels, the probability of J equals 6/10. There are 4 tiles with letters that come after L in the alphabet. So probability of K is 4/10. So what is the probability of J or K? So if we just blindly apply the addition rule, we get 6/10 plus 4/10 equals 1, which would mean that the compound event J or K is certain. However, it's possible to draw a B, in which case neither J nor K happens. Where's the error? The events are not mutually exclusive. The outcome U belongs to both events, and so the addition rule doesn't apply. However, there's a way to extend the addition rule to allow us to use this probability anyways. It's called the inclusion-exclusion principle. In this example, if we just add the 2 probabilities together, the outcome U is included in the sum twice. It's one of the 6 outcomes represented in the numerator 6/10. And it's one of the 4 outcomes represented in the numerator 4/10. So that particular outcome has been double counted. Since it has been included twice, we can get a true accounting by excluding it once. We can generalize this idea to a formula that we can apply to find the probability of any compound event built using OR. So if E and F are events that contain outcomes of a single experiment, then the probability of E or F is the probability of E plus the probability of F minus the probability of E and F. So you're about to roll a special 6-sided die that has both a colored letter and a colored number on each face. The faces are labeled with the following: a red one and a blue A, a red one and a green A, an orange one and a green B, an orange 2 and a red C, a purple 3 and a brown D, or an orange 4 and a blue E. Find the probability of these events. The number is orange or even. So how many even numbers do we have? 1, 2. How many orange numbers do we have? 1, 2. So the probability of orange is 2 out of 6. The probability of even is 2 out of 6. And the probability of orange and even, note they both are the same, is 2 out of 6. So using this formula, we would have probability of orange or even equal to probability of orange plus the probability of even minus the probability of orange or even, which would be 2/6 plus 2/6 minus 2/6, which would be 2/6 or 1/3. The letter is green or an A. Let's see. I have an A, and I have another A, a green A. Do I have any other green or A's? That's it. Wait a minute. Number 2. Green or an A? Oh, here's another green. Red, blue, green, orange, red, purple, brown, blue. So I have 2 greens and I have 2 A's. So the probability of a green is 2. Out of 6. Probability of an A is 2 out of 6. Probability of a green and A, well, we have this one here, equals 1 out of 6. So now I'm looking at 2/6 plus 2/6 minus 1/6, which is 3/6 or 1/2. Okay, the number is even or the letter is green. So we have 2 greens. And we're looking for an even number. 1, 1, 1. Here's an even number, and there's one even number. Nope, 2 even numbers. However, this is not green, and this does not have green. So we have 2 of each. Probability of even is 2 out of 6. Probability of green is 2 out of 6. Probability of even and green is 0 out of 6. So we're looking at 2/6 plus 2/6 minus 0/6 equals 4/6, which is 2/3. And that finishes off this section.